Hello and welcome. In this video, we're going to look at this specific sine wave here that has an RMS value of 20 volts and it starts at 0 degrees. So that means it starts right here at the 0 degree mark and that its RMS value, which we know is somewhere in the middle of average, is going to be 20 volts. So that's not the peak value, that's RMS. Right? It says calculate the instantaneous value at each of the following angles. Sounds pretty intimidating, but what they're actually asking for is this second number over here, right? That's going to be our rectangular form digit that we can pull out of that. So that's what we're going to get. So the first thing we need to do is to update our RMS value of 20 volts RMS to a peak value so that we know what this A is here. And this A is just going to represent some kind of amplitude, and it can be voltage or current. And we'll find that the voltage and the current kind of follow each other in these situations. They can be shifted a little bit from each other, but overall their amplitude, rise time and fall time, will be at the same frequency. Right? So we expect them to copy each other a little bit. So let's find our peak voltage of the 20 volts. So we'll take our 20 V RMS and divide it by 0.707. And that should give us our peak volts, VP. So VP is equal to, and we want A to equal VP. Plug that in here, and we'll say we have 20 divided by 0.707. That gives us 28.28, so 28.3. We'll say VP is 28.3 volts. And so that's what we expect A to be. All right, so the instantaneous value is when we have an angle that we want to know the specific voltage level at. And we see that at 0 degrees, we see our theta down here leads us all the way across. So our theta is this angle, right? And so if we say 30 degrees, we might be marking that angle off really early on here. We might say that this is 30 degrees, and that leads to this voltage value here. And so we'll solve for that voltage value, right? But we might have other ones here. We have one that is at 150 degrees, right? And so we'll find that to be over on the opposite side over here, 150. And so that will be the Y value for that stage. And so we'll trace that all the way back over to the other side here and get the Y value for that, right? And we can keep going for each one of these. The 210, that one's going to be somewhere over here. And we'll see that that crosses up here and we'll get the Y value for that one. Right? And then we'll have that last one here, which is 330. And so that's going to be somewhere on the other side here, 30. And we'll get that Y value there. So we're seeing something here. They're all kind of lining up. They're lining up along right here. And these two right here will line up. And so when we look at our plot over here, our unit circle, we'll see that the 30 degrees mark, we can line out. We can say this is the 30 degree mark here. And so that would be this value at 1/2. Right? That's the magnitude we're looking for. And so we can do each one of these. We can say that the 151 is over here. This mark over here, 150. And that's going to give us this 1/2. And that's the number we're kind of looking for here. We need it in terms of our voltage, but that's what we're going to aim at. So the way we calculate this 1/2 is going to be the way we calculate the instantaneous value at a specific angle. And so that's going to be the parallel we're trying to draw here. The 210 here is lined up at the bottom here. So we'll say 210 is this line here, and that is our negative 1/2. And that's the number we're looking for. Then the last one here, the 330, is at the back end here. 330, and well, that's negative 1/2. Right? And so that means that this rotation that we have in here is actually correlated directly to our map here. The 30 degree one is in the first quadrant of our unit circle, and that's going to represent this first half of the circuit over here. We'll see that the second half of the circuit is the 150 mark, and that's going to be this portion right here. Right? That's going to be that second quadrant of our unit circle. We'll see that this bottom half here is the pink part, and we'll have that be from the 0 axis line to the 90 degree mark here, and that's going to be our third quadrant. We'll have one more quadrant in our unit circle here that leads us to a full rotation, And that is going to be from the last bottom 90-degree mark to our 0 again, and that is our 360-degree line, right? And so that means that is the final portion of our cycle. And so our cycle rotates for a full 360 degrees before it begins again and rotates through. And that's the same moment that we begin around the circle again. Right? And so that's the parallel we're trying to draw here. So let's clear out most of this here. We'll leave a couple of these. And we're going to calculate out our instantaneous voltage at each of these voltage value angles. So we'll say that the 30 degrees, we want to get the imaginary number because we're talking about our imaginary axis, which is the y-axis here, right? Our x-axis is going to be our theta value, and our y-axis in this case is going to represent our voltage, but it can represent our current also, and a couple of other values that we can put on there as well to compare. So these types of charts are going to be very useful for us. So we'll take our 30 degrees, say that we're looking for, in rectangular form, we call this A plus or minus J, plus or minus JB. And we're actually looking for the JB part. Right, so we're going to say that our B variable in our rectangular to polar form conversions said that B was equal to the C sine of theta. And in this case, our C is actually our V. And so we can replace that and say, well, this is going to be our voltage sine of theta, specifically the peak voltage of our signal. So that's what we're going to use here. We're going to say that the instantaneous voltage that we're looking for at 30 degrees, so V 30 degrees, is equal to the peak voltage, 28.3, sine of 30 degrees. So make sure your calculator is in degrees for this one. So let's send this out, and we'll do that. We'll say that we have 28.3 sine of 30 degrees. Again, make sure your calculator's in degrees. Anytime you're doing sine, cosine, tangent, inverse tangent, all those all need to be in degrees. And if we flip it out of degrees, we'll see that it's a different number, right? That number doesn't really make sense for our signal here because we're not at the peak. That number would represent at the very, very peak of this signal here. And we know that we're way down here at this bottom mark down here, this green 30-degree mark. And so that means that that can't make sense. We got to make sure we check the radians of our signals here. So 14.5, that means that we have rose 14.5 volts to get to this mark here, and that this Y is equal to 14.5 volts, 0.15 volts. Right, so we'll write that in for our voltage up here. We'll say that V30, V of the 30-degree angle, is equal to 14.15 volts. And we could do that for each one of these. So we'll do the same thing. We'll say that the next one, send this out here. We can even copy and paste this equation in for the next one here. And just watch out the 30 for the 150 because our magnitude stayed the same. We'll say 150 here. Look at that. We're at the same angle. And we kind of expected that. If we compare our unit circle here, we see that we're kind of at the exact same spot on both sides of those quadrants. And so that's what we expect. That 1/2 matches. Right? And so we'll write this in. This is our V 150 degrees is equal to 14.15 volts. Right? And that means that we have rose and fallen from our total peak voltage. Right? We're looking at it right here. We've rose up to our peak voltage and come back down before we actually looked at this signal again. That means that this Y right here is the 14.15, right? It's on its downward slope though. Before it was on its rise, now it's on its fall, but they're still the same value. Right? We pinned it at the same moment on either side of our sine wave. And so we can do that again for our next signal here is 210. So we can just swap out this one here and say that we want to go 210, 210. And that gives us a negative, right? So the V 210 degrees is equal to a negative 14.15 volts, right? That tells us it's on the bottom down here. That's that negative side of it. It tells us it's on the bottom side of our line of 180 degrees. 180 degrees is that flat line right there, right? We see that over here with that 180 pi. And so that tells us that we're on the bottom, we're on the underside of that, and that is the negative rotation of our axes over here. So same magnitude though, right? Because we pinned it at the exact same point. like we've flipped it over and we're kind of marking the same exact locations of the sine wave just on different sides of the unit. Okay, so we'll do one more here and we'll see that we got 330, and that gives us another negative 14.15. The 330 degrees is equal to negative 14.15, right? These two are still different, right? The first one, the pink one over here, was on our rise up to our negative peak, and we know that's going to be negative 28.3 volts. And then on the other side, we get negative 14.15 again, but that's just because it's on our falling edge here. So this one's also negative 14.15, and it's going to continue down until it hits 0 volts at this axis again, and then it's going to do it again. It's going to start over at the very beginning and rise up until it hits the same sequence over and over again. And that's the glory of our sine waves. We can predict them. And a lot of times we'll cut them in half because we know the bottom half of the signal matches the top half of the signal. And so when we go for more complex calculations for sine waves, we'll end up splitting in half a lot of our signals. Great. Let us know if you have other questions.